Carbohydrates are simple sugars, monosaccharides, or polymers thereof. So if we took those simple sugars and sort of put them in a big long chain, shorter chains would be oligomers, and longer chains, or oligomers, or oligosaccharides, or just oligos. And then longer chains would be polysaccharides. So we can classify most monosaccharides as either ketoses or aldoses. And the names kind of give a hint of what we're looking at. So ketoses contain a ketone in the chain, and aldoses contain an aldehyde. There are 8 aldohexoses: allose, altros, glucose, mannose, gulose, idose, galactose, talose. If you're trying to memorize them, and I don't recommend it, but if you are trying to memorize them, the typical memorizing tool is all altruists gladly make gum in gallon tanks. Now you know. The most important of these by far is glucose. So we're going to spend some time just talking about glucose. In most textbooks, you'll see glucose drawn like this. This is a really old way to show stereochemistry called a Fisher projection. In a Fisher projection, you always read the cross ties as little bow ties. So all of those horizontal lines are coming out at the viewer, and all the vertical lines are essentially going back, right? So imagine if a caterpillar was doing a back bend or something, and you're looking at the caterpillar's stomach, or the millipede. It's gross. Here's perhaps a more useful way to draw and remember glucose. So here it's kind of like a cyclohexane ring, and notice that when I draw it like this, everything ends up in the equatorial position, even the CH2OH over there. So what we're going to see in glucose is that it really wants to cyclize. Much less than 1% of glucose actually exists as this open chain aldehyde. Most of the time, an OH group here is going to form a hemiacetal. I can do that one of two ways depending on which way this aldehyde is twisted. I'm making a new stereocenter, and it could be with either of those configurations. And so we'll call that the anomeric carbon. That's kind of a special carbon. We'll call these two anomers of each other. It's just another, it's a very special kind of diastereomer. And so these are all in equilibrium with each other. So typically if I put glucose into a pot, you're going to get about 64% of this, what we'll call the beta anomer, where this OH ends up equatorial, and about 35% of the alpha anomer, where that OH ends up axial. And I think that's the best way to remember it: A alpha, A axial, right? So the alpha anomer is where it's axial. Lots of A's. Okay, let's get to the reactions of carbohydrates now. So remember that these carbohydrates are hemiacetals. Usually we said that hemiacetals are not stable. They just want to break up into alcohol and carbonyl compound. But in this case, a hemiacetal is going to be stable because it's cyclic, right? I'll always have the aldehyde and the alcohol kind of stuck near each other where they can react interchangeably. Right, but even so, I'll draw that squiggly line because it's constantly opening up and reattacking, and every time it attacks, it could either give one enantiomer or one diastereomer or the other. Okay. Now, if I take this hemiacetal and I cook it in alcohol in acid catalysis, I'm going to get an acetal, and the mechanism is exactly what we talked about in that video. An acetal of a carbohydrate is called a. To briefly touch on how the mechanism works, we can imagine opening up to this aldehyde, using our acid catalyst to protonate that aldehyde to make it a better electrophile. Our nucleophile here is methanol. It's a weak nucleophile, but it's good enough. We'll attack here. We'll get some, I guess this is also a hemiacetal here, but then we can also use our acid catalyst to make this OH a better leaving group. So if we add acid and we remove water, then we get to this very, very reactive electrophile, which can then get closed back up as we reform our acetal here. So again, most carbohydrates hang out in hemiacetal form, but if we cook them with an alcohol and acid catalysis and remove water, then we're going to make an acetal, which we're going to call a glycoside. Carbohydrates react like aldehydes. This is xylose. It's different than glucose because it's missing that CH2OH on the top, right? So it's a 5-carbon, not a 6-carbon sugar. This is reduced with sodium borohydride. The product of this reduction is xylitol, this thing, which is can also be drawn like that. Xylitol is a commonly used sweetener that doesn't contribute to tooth decay. So if you have sugar-free gum, it's probably sweetened with xylitol. It's supposed to be really bad for pets, is what one vet told me once. But how does this reaction work? How should we think about sodium borohydride reacting with this thing, right? At first glance, this just kind of looks like an ether, and so it doesn't look very reactive to hydride. But remember, every carbohydrate is, once in a while, an aldehyde. So xylose is continually opening and closing to give its open chain aldehyde form. So if we're in the open chain form here, we can see this aldehyde, and if we remember how sodium borohydride works, it's very reactive toward aldehydes. This hydride can just get delivered there. Okay, so carbohydrates, really, really important molecules, pretty complex molecules. We should A, be able to recognize glucose because that's the most important carbohydrate, and B, understand that the chemistry of carbohydrates is essentially the chemistry of aldehydes.